The previous week of lectures, we were able to understand the magnetization that arises due to presence of nuclear spins in a sample gets affected by the magnetic fields that are applied as they experience a torque. The rate of change of magnetization is given by the cross product of M cross B effective with a gamma, where the B effective comes up due to the external magnetic field B naught and the RF field that is applied. This RF field is composed of the amplitude B1 and the oscillation frequency omega RF. This omega RF, when set slightly different from that of omega naught for a given spin, results in an offset which is given by omega naught minus omega RF. We also understood that the B effective in the rotating frame is given by B1 cos phi times I plus B1 sin phi times J and delta B naught times K. All the unit vectors in this case are in the rotating frame. The relationship between gamma and delta B naught is given this fashion. If we write our magnetization also in the form of a vector mx I cap, my j cap plus mz k cap, then we would be able to get what is dm over dt, which is given by the cross product of m cross b effective, which will be given by the determinant I, j k, mx, my, mz, and you have gamma times b1, that will be minus omega 1 cos phi minus omega 1 sin phi and minus capital omega, because you have a gamma delta b naught, the negative sign, that will be minus capital omega. So now this can be written as or simplified as mx times my times minus gamma plus mz times omega 1 sin phi minus j times mx times minus capital omega plus omega 1 cos phi times mz plus k times minus mx omega 1 sin phi plus omega 1 my cos phi. Therefore, we are able to see this will be the dmx over dt given by minus gamma my plus omega 1 sin phi mz. dm over dt will be the y component, that will be this component, and dmz over dt. So all that has been done is to decompose the dm over dt into its mutually orthogonal components. Bloch also introduced ad hoc the relaxation process. The way he related it is very similar to the first order kinetics, where he said how much ever is remaining in the transverse plane will decay as a function of time with a rate called R2. I would like to remind you that R2 is given as 1 over T2. And similarly, since My magnetization is also transverse in nature, it will have the same R2 rate, but of course with respect to My. However, on the other hand, Mz, which is due to the polarization that is present, has a different rate, which is R1, and unlike the case of transverse magnetization where you have decay that is attributed with a negative sign, here you do not have a negative sign, largely because this is recovery of the longitudinal magnetization. That will be given by how far it is from M0, that is at equilibrium. Therefore, these get directly plugged into these equations, where you have minus R2 mx minus R2 my plus R1 m0 minus mz. So this whole equation can be written in a matrix form, that is d over dt of mx my mz will be given by, let's write the matrix form, is going to have mx my mz So what is the mx component here? Minus r2. What is the my component here? Minus omega, capital omega. What is the mz component? Omega 1 sine phi. Plus r1 times m0 0 0 1. This factor ends up coming because you have r1 times m0 that is only present as a function of z. And of course, it's also coming only in the third component, which is due to the presence along z. So this equation or the matrix is called the Bloch equation. Of course, it also includes components of relaxation in it. And at the same time, you are also able to appreciate the fact it has the information of the pulse that you apply as would come in omega 1. And also in terms of offset, which you will understand in a moment, which will help you get the chemical shift. Remember, if you are applying a pulse along omega RF, if you are able to determine what is capital omega, you will be able to say what will be omega naught. So that is the whole purpose. If you are able to determine what is this capital omega, you would be able to determine the Larmor precession frequency of the different spins that you might end up having. So let me rewrite some of these equations. You are able to understand an important aspect here. The signal that we end up detecting will be along mx and my. So therefore, if you are trying to set the receiver along the transverse phase, basically you will end up measuring how much is the amount of mx and my that is present. However, one has to be careful in measuring this because you are able to see the rate of change of the x component is mutually connected to the y component as well. It also has a part of z component, which will come in a moment. And y component therefore also has a combination of mx that is going to be present. Let us take a simple case, case 1, where you have a magnetization that is present. You can always take it as any magnetization, meaning that m is not the equilibrium magnetization. So therefore m is going to be given by mxi plus myj plus mzk. The magnetization could be pointing along anywhere within the three-dimensional space. The first case is one where no RF pulse is applied. When no RF pulse is applied, you know that omega 1 is equal to 0 because B1 is equal to 0. Therefore, what will end up happening? The omega 1 terms will vanish from the rate of change of the transverse magnetization. And since you are setting a coil along the transverse plane, it's not mx or my that you measure. You end up measuring m plus or m minus. So for the sake of simplicity, let's go with m plus. This is very similar to the ladder up operator that you would have seen. So therefore, dm plus over dt in the absence of an RF pulse would be equal to x component, which is minus capital omega my minus r2 mx plus I times I omega capital omega mx minus I r2 my dmx over dt plus I times dmy over dt. So as to get dm plus over dt. I omega out common, you have mx plus I my This is not a surprising equation for you because you've already seen it. dm over dt goes as a function of how much ever m is present. Since it's transverse magnetization, how much ever is present, you're going to have that being modulated. When you integrate it such that your t goes from 0 to t to acquisition time, so for sake of simplicity, I'm going to say you integrate between 0 to t, you're going to have dm plus over m plus equal to 1 over omega minus r2 times dt. Essentially what you're trying to see, how does the signal look along the transverse plane. So therefore this is going to be ln of m plus is equal to I omega minus r2 times t plus a constant k. Here, the constant k would be determined by what was the amount of magnetization that was available at time t0. So meaning that, let's say you applied a 90-degree pulse at t equal to 0, you're going to have k is equal to ln of m plus of 0, meaning the magnetization that was available at t equal to 0. So therefore, m plus over m plus of 0 will be equal to e power I omega t times e power minus r2t. So this implies you would get a signal m plus will be given by m plus of 0 times e power I omega t times e power minus r2t. We have to plot them to understand them better. E power I omega t is nothing but, so if you would like to plot it as a function of time, remember this will be a 3-dimensional plot. I'm just doing it in 2 dimensions in order to make sure we are able to see. Cos function will start with a maximum and will go through 0 at a certain time. So this will be one full cycle. On the other hand, the sine would be a function that looks like this. Basically, the 0 crossing would be the maxima or the minima for the cos function. In a 3-dimensional plot, you will be able to see it basically inscribes a helix. This provides the oscillation with respect to the offset that is present. So somehow, once we get the signal, if you are able to pick this information, you've got the chemical shift of the entity that you're working with. Remember, your omega is going to be given by omega naught minus omega RF. Since you know what you supplied, if you get this, you will be able to get your chemical shift, the alarm precession frequency from which you can get your chemical shift. On the other hand, the function that you're seeing here is relaxation. So let us plot this function as well. Let us say you have e power minus r2t within the same plot. Of course, it won't go from 1, it will go from m naught, but just for the sake of simplicity, I am drawing within the same curve. E power minus r2t will be an exponential decay. Okay, so to redraw it, when you have t, let's say you started with a maxima, in this case, let's say it's normalized to 1, you're going to have a function that decays over time. You have a function that decays over time. Now, of course, e power minus r2t tends to 0 when t tends to infinity. So once you are able to see this, you are able to understand how the signal looks, which is what you would see in most of the NMR depictions. This is as a function of time, what you're measuring is m plus. So this will be something like m plus of naught, whatever the signal maximum was at time equal to 0. And there are 2 components that go here. The decay part, that will be e power minus r2t, and oscillation part. You are able to see this is the oscillation part. Of course, in this you will be getting the time period. From time period you can get the frequency. From frequency you can therefore get the offset. We are of course showing a plot here for a single case, let's say for water, where the carrier is not set to this water proton. The advantage of acquiring the signal this way is that when you perform something called Fourier transformation, this oscillation, meaning e power I omega t, will end up giving you a Dirac delta function at omega, and this e power minus r2t results in the line broadening. We'll see how the function looks in a moment. Product in the time domain will be convolution in the frequency domain. So let's take a look at all of this in a pictorial fashion. Dirac delta function at omega will give you a plot something like this, nothing in minus omega, and the Fourier transformation of minus r2t would give you a function r2 divided by r2 square plus omega minus omega the whole square. So essentially this will be a function So this function is called the Lorentzian, which provides you the line shapes for the resonance that you're trying to look at.